Hello and welcome back to my calculus lecture series. Today we will be covering Chapter 3, dealing with derivatives. The sections we are going to be covering are derivatives of a function, differentiability, rules for differentiation, velocity and other rates of change, derivatives of trigonometric functions, the chain rule, implicit differentiation, derivatives of inverse trigonometric functions, and finally, derivatives of exponential and logarithmic functions. We will start with section 3.1, where we will talk about derivatives of a function. We will be covering the definition of a derivative, notation, relationships between derivative graphs, and one-sided derivatives as well. Now, what is the definition of a derivative? Well, it's the following. The derivative of the function f with respect to the variable x is the function f prime whose value at x is the limit as h approaches 0 of f of x plus h minus f of x divided by h. Now that definition probably raised more questions than it answered, so what does any of this actually mean? Well, to help explain it, I'm going to pull up this very handy visual. Here we have a graph of a certain function, let's call it f of a, and you can see that function in the green. In the gray we have a secant line. The slope of the secant line is delta y over delta x. What does that slope tell us? Well, it tells us what the average rate of change is from point A to point A plus h on the x-axis. Now let's see what happens when we move point A around. So we have our average rate of change here, and again our secant line, which is the gray line, is the average rate of change over a certain interval from A to A plus h. Now, that average rate of change, the slope of the secant line, can give us a pretty good idea of what's going on in that interval, but it's not really that accurate. So let's take a look. If we go like right here, we notice that our secant line is a straight line, and our function f of a, which is the green curve, is a curve. So while the average rate of change can give us a pretty good idea of what's going on over the interval of a to a plus h, it doesn't really tell us the full picture of what goes on between a and a plus h. And just a side note, you can kind of remember that h is basically the value of delta x. It's what number x increased by over the interval delta x. Now let's say we wanted to get a more accurate average rate of change. Well, naturally what we have to do is reduce the value of h so that we're dealing with a small interval. And let's see what happens when we do that. So h is equal to 1.8, 1.7, 1.4, down, 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 until we get a much smaller delta x value. Now what you can notice is that secant line is hugging the green curve a lot closer. It's a lot closer to the green curve, so there's not much of a difference between the gray line, which is our secant line, and the green curve. As we make this value of h smaller and smaller, we get closer and closer to that green curve. Now what happens when that value reaches 0? Well, unfortunately, we have 0 divided by 0 up here, so we have an undefined value. Now, theoretically, if you could take the average rate of change of this green function and have the delta x value, the h value, be 0, you could get a 100% accurate picture of what's going on, what the instantaneous rate of change is at that point. However, we are limited by the fact that if this were the case, if h was equal to 0, we would be dividing by 0 in this equation up here. So how do we resolve that problem? Well, instead of having this equation up here, we use this equation over here that states that we're not dealing with this term alone, but we're dealing with the limit of h as it approaches 0. This solves the problem for us of dividing by 0. Because remember, we want that interval, that delta x, to be as small as possible. We want it to be 0, but we can't go directly to 0 because then we'd be dividing by 0 and we'd get an undefined number. So instead we have to resort to saying, as we approach 0, as we get infinitely close to 0, that's going to be the size of our delta x. Now, if I make the h value larger, we have a secant line, meaning that we have this straight line where it's crossing our curve at two different points. However, as we get closer and closer to an h value of 0, our line is no longer a secant line. If h were equal to 0, or rather the limit as h approaches 0, then this line would no longer be a secant line. It would be a tangent line, meaning that it only touches the curve at one point and not two. Sometimes people struggle with the idea of what a tangent line to a curve actually is. And if you have a little bit of difficulty visualizing that, try imagining this. You have a curve and a really small car that's driving over it. Now, the line created by the two wheels is going to be the equivalent of the tangent to that curve. For example, I always had a hard time picturing, how do I visualize the tangent to the curve, let's say at this point right here? Is it going to be like this, or like more like this? It's a little bit hard to see, but if you use this visual tool right here where you have the car traveling, a really small car traveling over the curve, and you have a line that's formed parallel with the bottom of the car, that's a really good way to visualize the tangent to a curve. And the whole purpose of this is to find instantaneous rates of change versus average rates of change. So we have two graphs here at the bottom. We have the one on the left, which has a secant line right here, secant line, that crosses the function at 2 points, point A and point B. And the slope of this secant line, delta y over delta x, the slope value of that line tells us what the average rate of change is over that interval. Now, if you look at the x and y axis, we have time on the x-axis and position on the y-axis. Now, what would the units be for the slope of that secant line? Well, since we're dividing rise over run, the slope would be, the slope's units would be meters divided by seconds, or meters per second, aka velocity. Now, since it's an average rate of change, or average velocity, we have an interval. Now remember, the smaller and smaller this interval right here is, the more accurate picture we get of what the velocity is in that interval. Now, if our delta t value was infinitely small, limiting to 0, we would get a tangent line like we have here on the right instead of a secant line. And the slope of that tangent line wouldn't give us the average speed, it would give us the instantaneous speed, what the actual speed is at any point in time. Now you may ask yourself, why is this useful? Why do we need to know the instantaneous speed rather than the average speed? Well, let's take a look at this picture up here in the right-hand corner. Imagine two different scenarios. We have one scenario where a car is traveling on the highway at 60 miles per hour or 100 kilometers per hour, and a second scenario where a car is stuck in traffic for half of its journey, and then for the other half of its journey it's going 120 kilometers per hour. The average speed for both situations would be 60 miles per hour, or 100 kilometers per hour. However, that doesn't really tell us a whole lot about the actual journey of the car. Was it stuck in traffic and then drag racing, or was it going a constant speed the entire time? The average speed is not going to tell us that. However, if we find the slopes of the tangent lines at each point on this curve, we can know at that moment what the actual speed of the car was, which gives us a much bigger, much more clear picture of what's actually going on. Now let's talk a little bit about the notation used for derivatives. Say we had a function called y, and we wanted to know what the derivative function of y was. Well, one of the ways we could show that is by writing y prime, y with this little apostrophe. Now the benefit of this notation, and there's a lot of different notations, each one of them is a little bit different and each has its benefits and drawbacks, but the benefit of y prime is that it's nice and brief. However, its drawback is that it does not name the independent variable. So let's say you had a function y of x or y of t. Well, if you just have y prime, you don't know what the independent variable is. It doesn't actually say that. Now the next notation, this is also called Leibniz notation, is probably the most common one that we're going to be seeing. Now you may notice that it looks a little bit like a fraction, and it actually does behave like a fraction, as we will see later on. It's not technically a fraction, but it does have all the same characteristics of one. Now the benefit of this notation is that it names both variables and uses d to show you that it's a derivative. Now whatever value dy, in this case it's dy, we have on the numerator, that's the function you're taking the derivative of. And on the denominator we have dx. That's the independent variable that we're taking the derivative with respect to. Now don't worry about that too much right now. We'll talk more about what that means later. Another couple of notations you might see is this one right here, df of dx, and this one emphasizes the function's name, so it's saying that you're taking the derivative of the function with respect to x. And the last notation you might see is this one right here, where we have ddx of f of x. Now, this is kind of the same thing. It's saying the same exact thing as the one above, but it just pulls the f of x out front. This one shows the most amount of information, but is relatively uncommon. Now let's say we have a function, let's call it f of x, here on the left-hand side. And then we wanted to know the instantaneous rates of change at points A, B, C, and D. Well, to do that, we just draw tangent lines at points A, B, C, and D. I apologize for the bad lines. It's a little bit difficult drawing them with a stylus. However, just imagine that these are straight tangent lines at each of these points. And as we can see, the slope of the tangent line at point C is 0. The slope of the tangent line at point B is 1. The slope of the tangent line at point E is -1. So let's just say that we had a tangent line at every possible point on the x-axis. Well, we could graph the slopes of those tangent lines and create a new curve, a new function that we call the derivative function. As you can see, right here we have y, otherwise known as f of x, and here we have y prime. This is the derivative function of y. So if you take a look, point B, right here, point B on this curve right here corresponds with the slope of this tangent line at B on this original graph. Point C, where the slope of the tangent line is 0, corresponds with point C right here on the derivative function graph, and so on and so forth. Next, we're going to explore some other common functions that we might see and what their derivative graphs would look like. So if you take a look here, in the blue we have function f of x. And we have, where my cursor is going, we see several different tangent lines being formed. So wherever I drag my cursor, we have a tangent line that has a different slope. Now again, just as we were talking about before, what happens when we graph each of these slopes of these tangent lines on a separate graph? Well, we can see that down below in g of x, which is the derivative function of f of x. So here, down here in this red line, we have the slope values at each point of function f of x. So take a look. When I get to the vertex of f of x, I have a slope of 0 for my tangent line. And if you look at the graph on the bottom that's in the red, we see that right there it crosses the x-axis. The value is 0. So again, f of x on top, and on the bottom we have the derivative function of f of x, where we plot each of these individual tangent line slope values. So this is kind of the relationship between the two. Now here's another interesting example. We have a very simple function, f of x is equal to x. Now if I follow this function up, I don't really see any tangent lines, and that's because the tangent lines are just on top of the function f of x. So the slope of each tangent line is going to be the same no matter where I am here, which is why the bottom derivative function is just a constant value. Now here's another interesting example. Let's say I have the function x cubed. Now notice as I go along this function that the slope of the tangent line is always positive until we get to 0. And then it becomes positive again. Now if you notice, on the bottom we have the derivative function. Now the derivative of x cubed looks just like a normal parabola. And notice that every y value for the derivative function is above the x-axis, is positive. That's because no matter where I go on x cubed, the slope of the tangent line is going to be positive. And we also notice that right here, where the slope of the tangent line is 0, where it's flat, we reach the vertex of the parabola on the bottom, whose y value is 0. Now sometimes we have an interesting case where we have one-sided derivatives. Certain functions are a little bit strange, and we would have a different derivative whether we're approaching from the left-hand side or the right-hand side. For example, let's take a look at this graph on the right-hand side. It kind of looks like the left-hand side of this function is a parabola and the right-hand side of this function is a straight line. And interestingly, the derivative on the right-hand and left-hand side are different. If we approach the derivative at x equals 0 from the left-hand side, we get a tangent line with a slope value of 0. However, if we approach the point x equals 0 from the right-hand side and take the derivative at that point, we have a slope value of what looks like m equals 2. So we have two completely different slopes of the tangent line depending on which side we approach x equals 0 from. Now, technically, the function isn't actually differentiable at x equals 0 for that reason, because if we approach from different sides, we get two different derivatives, two different slope values. So at x equals 0, this function is non-differentiable. However, at any other interval, it is differentiable. For example, if we wanted to know what the derivative is at x equals -1, we could find it pretty simply. Oops, one moment. We could just draw a tangent line like that. Or if we wanted to know what the derivative of the function is at x equals 1, we could draw a tangent line there as well. So let me do that as carefully as I can. Something like that. And so at those points, this function is differentiable. However, at x equals 0, it is not, because you'd have a different slope value whether you're approaching from the left-hand side or the right-hand side. This is just one example of where a function might not be differentiable at a certain point. We'll see a lot more of these examples later on.